So continuing with introducing a number of functions in order to us to begin using them to model. The focus of this is all on exponential functions. And an exponential function is in general any function in which your independent variable is in the exponent and your base is a constant. And one of the most common bases we use in exponential functions is a base of e, which you may recall is approximately 2.718. Especially in calculus, it's quite helpful to think of exponential functions with that base. That's it, regardless what the base of the exponential function is. Anything in this form, if e is any other number greater than 0 and not 1, it has one of two sort of features. But most exponential functions, if the base is a number larger than 1, such as e, it looks something like this, where it never touches the x-axis. So we have a horizontal asymptote on the x-axis. It always crosses the x-axis, the y-axis at exactly 1, and has this sort of shape right here, our sort of classic exponential growth curve. And keep in mind, if the base was between 0 and 1, like a base of a half, it would be a horizontal reflection of this. It would look something like this, what we call a decay curve. Although when we think about exponential functions, we tend to think of growth, although we shouldn't exclusively think of that. And if I just look at my quick sketch, and I'll go to Desmos here and kind of show what it looks like in Desmos, there is e to the power of x, pretty standard. Notice it never quite touches the x-axis, because you can't raise a number to a power and get 0. You can get infinitely close to 0, but you can never actually get exactly to 0. So if I just now add 2 to this, then this whole graph just moves up 2. So this horizontal asymptote is now 2 above the x-axis, and the y-intercept is now 3 above, but it's still the same shape as before. If I change the input from x to negative x, that means all my x coordinates are changing sign, which in practice for the graph causes a reflection about the y-axis, or horizontal reflection, or as I'll show here. For example, here was a previous graph with the asymptote shown, and here is the graph we're looking at now. Notice it's the same shape if we just reflect it about the y-axis, and we call this a decay function. And so that will generally always happen if we change the sign of x to a negative, or multiply x by -1. And so it now looks like this. And again, the y-intercept has been moved up 2 from the first example, so again, it's at 3. And lastly, if we have a exponential function where we, instead of multiplying the x by a negative, we multiply the whole exponential function by a negative, so it's negative e to the power of x, or you can think of it as -1 times e to the power of x, then we still have our horizontal asymptote at 2, but now e to the power of x has been reflected vertically, so it looks something like this, where that y-intercept is now 1 below the horizontal asymptote, so at +1. And again, I'll show it here in Desmos. There we go, right there. In fact, I'll compare that to e to the power of x plus 2, and you see in red, negative e to the power of x plus 2. Same idea, except it's now being, we say, reflected vertically. And later on in the course, we'll talk more about transformations in general of these functions. All right, although, of course, while it's ideal that we can visualize as much as possible without having the graph, you always are able to use your GDC to graph a function. But if we do that every time, if we don't have that intuitive sense of how a function behaves, we end up spending way too much time just graphing things, which is not really the point. All right, here I have an exponential function. I want to figure out what the equation of this exponential function is. Well, first of all, what I can see is that I have my asymptote is right here. And so my asymptote is at y equals 4. So far, what I know about my equation is that I said this is the basic form of it. K, some coefficient times my base, the power of x plus c. Well, I know that plus c must be a 4. It's been moved up 4, so I'm going to change that to a 4. All right, so I can tell that right away. Now, what's left is to try to figure out what a and k are. K being the coefficient and a being the base. In the last question, the base was an e. Keep in mind, an exponential function, the base is always a constant. So we need to figure out what that constant is. So to figure that out, I need to look at these other points. And for example, if I look at what I have here, a fairly common idea is if I can find a point, for example, 1, 10, then I know when x is 1, y is 10. So even though I don't have the most detailed equation here, I know if I replace x with 1 and y with 10, I get an equation that is correct. So I'm going to take this equation, instead of y equals, I'm going to say 10 equals k times a to the power of 1 plus 4. So I know this must be true. And so focusing on this, that means 10 equals k times a plus 4. If I look at this, I'm kind of stuck for a moment. So, because I have two variables here. And so let me look at a different point. If I can find one more point, I can figure out some more. Because if you look at this equation I have two variables with one equation. But here's another point. I can see the coordinates of it quite nicely. This is at 0, 5. Which means I know when x is 0, y is 5. So the same idea I'll do right here. Instead of y equals all this, I'll say 5 equals k times a to the power of 0 plus 4. Now this is a little more helpful because a to the power of 0, anything to the power of 0 is 1, as long as a is non-zero. And so I know a is not 0, otherwise we wouldn't even have a graph. So I know I can say 5 equals just k times 1 plus 4. Or just 5 equals k plus 4, which means subtract 4 from both sides, k must be 1. And so now that I know k, I can go back to what I had before, and I can change that k there to a 1. So I have 10 equals just 1 times a plus 4. And so clearly I can now solve for a, subtract 4 from both sides, and so a must equal 6. And so now I know all aspects of my equation. So going back to the start, I'll take this, and now I'll write it as y equals 1, which I don't really need, times 6 to the power of x plus 4. So clearly, the most common way of writing it is just 6 to the power of x plus 4. All right, and just to confirm that I'm correct, if I just go to Desmos, turn all that good stuff off, and there's the graph. That's 6 to the power of x plus 4, which matches what we see in our notes. All right, last part. I have a function, I tell you the equation, negative 3 times 5 to the power of negative x, but we're only looking at a restricted domain from negative 2 to 2. So what's the range of this function? And is there a horizontal asymptote? If so, where is it? Well, one thing it's not a bad idea to do is to graph this function here. Y equals negative 3 times 5 to the negative x. Although when we graph it, we'll be seeing with a domain of all real numbers. Eventually, we only want a domain from negative 2 to 2, because keep in mind, any restriction like this is really telling you the domain. That's it. Let me go to Desmos again, turn all this good stuff off. And so this is the graph of the entire function. This doesn't take into account the restricted domain. And so we want to imagine this only exists on the x, in terms of the x coordinates, from negative 2 to 2. And so if I kind of compress this down a bit, I can see here's where, if I look at my cursor, here's where x is negative 2. Around here, up to positive 2. So it's just this chunk right here. So what are those values? Now I can use my GDC to find, where this begins and ends. It's probably easier just to do it algebraically. Because if I want to find out, what the range of this is, I need to figure out, okay, let's put in negative 2 and see what comes out. So instead of g of x, let's find g at negative 2. And I get negative 3 times 5 to the power of negative 2. Which is the same as negative 3 times 5 to the power of 2, which is negative 75. So I know when x is negative 2, which is where my function begins, the output is negative 75. And so let's do the same idea for positive 2. This is where my function is going to end. Keep in mind, if there was no restriction, this function would have no beginning and end. The domain would be all real numbers. And so negative 3 times 5 to the negative, now it's positive 2. And evaluate this, I get negative 3 times 5 to the negative 2, which, keep in mind, remember, is the same as negative 3 over 5 squared, or negative 3 over 75. Helps if I can do my math. Negative 3 over 25 is what I meant to say, and write down. And so keep in mind, when I put in positive 2, I get out negative 3 over 25. And when I put in negative 2, I get out negative 75. And this is the beginning. This is where my function begins. This is where my function ends. So essentially, I can see my range here. I can see that the range of this function, the range of g of x, I've called it, must be everything from negative 75 up to negative 3/25. And compared to trying to figure these values visually or using the graph, I do think this is considerably faster and cleaner, and we get to the exact values without having to trace or anything. Although, as a quick little visual, perhaps most important of all, is that when you see this question and you see the function and the restricted domain, we can kind of have a visual in our mind of what this must look like. Because really, the function that we're asked to visualize, which has a restriction from negative 2 to 2, doesn't look like this. It looks like just this. It's just this portion of the graph from negative 2 to 2. Which leads me to the last point. Does this have a horizontal asymptote? And no, this does not. A horizontal asymptote is when your function approaches some point and gets infinitely close, some point on the y, but never quite reaches it. This just doesn't. It gets close to 0, but it just stops right here. And so this function as it is doesn't have a horizontal asymptote, whereas this function does. This has a horizontal asymptote where y equals 0. This doesn't have a horizontal asymptote, although it would if we let it go on. So to finish that off, I'll just say, nope, no asymptote.